Hey folks, continuing on section in chapter 7, the next topic we're going to look at is improper integrals. This is section 7.6. In section 7.6, the objectives we are going to focus on is objective 1. We're going to evaluate an improper integral of the form integral a to infinity f of x dx. Objective 4, which is applying an improper integral to estimate total oil well production. And objective 5, applying an improper integral to fund what is known as an endowment. So to get started here, as the title of the section says, improper integrals, that's what we're going to discuss in this section. An improper integral, there are two main ways to come up with an improper integral. We're only going to focus on one particular way, and it's where one of the bounds on our interval continues forever. Here are some things that we would have seen back in chapter 2, some limits that will be very important for us to know in this section. So specifically, the limit as x goes to infinity of e to the x, that limit is infinity. The limit as x goes to infinity e to the negative x, that limit is 0. Also keep in mind e to the negative x can be rewritten as 1 over e to the x. So limit as x goes to infinity of 1 over e to the x, it too is equal to 0. The limit as x goes to infinity, natural log x, well, that limit is infinity. And the limit as x goes to infinity of any constant over x to the n is 0. So those are some limits that will be important for us to know in this section. All right, so to help us understand how we attack an improper integral, the methodology behind it, what we should be thinking, let's consider the function f of x equals 1 over x squared, and the improper integral, the integral from 1 to infinity, 1 over x squared dx. So what I'm going to do now is I'm going to head off to the board. I want to see the graph of 1 over x squared. So I'm going to head off to the board, and we're going to continue our discussion of how to attack this improper integral at the board. All right, hey folks, where I left off on the slide, I said we were going to consider the function f of x equals 1 over x squared. And how do we analyze the improper integral from 1 to infinity, 1 over x squared dx? So let me come all the way down here. That improper integral matches up with a picture that looks something like this. Here's the graph of 1 over x squared. So the integral from 1 to infinity, 1 over x squared dx, it's basically representing the area of the region that's below the graph of 1 over x squared, above the x-axis, from 1, and it continues on forever. Now I know part of your intuition might be saying that, well, if this region continues on forever and ever, there's no bound to it, that it would have an infinite amount of area. That might be part of your intuition, and it's not correct. And that's okay. When the concept of infinity is playing the game, our intuition can tend to let us down sometimes. So let's see how we would attack this improper integral. And we're going to do that by doing some simpler, easier, but related problems. So what do I mean by that? Well, let's look at this first picture here. Here's the graph of 1 over x squared, but I'm just looking at the interval from 1 to 4. You can write a definite integral that will find that area. You know it's the integral from 1 to 4, 1 over x squared dx, which I would rewrite as the integral 1 to 4 x to the negative second dx. Get my antiderivative, negative 1 x to the negative first Evaluate that from 1 to 4. I would probably rewrite that as negative 1 over x from 1 to 4. So we use our fundamental theorem of calculus and we get a negative 1/4 minus, well, that's what, minus a negative 1. So the area is 3/4. Easy, no problem. Let's do this one. Notice it's the same function, 1 over x squared. Let's find the area of the region from 1 to 10. Well, you know a definite integral to find that area is the integral from 1 to 10, 1 over x squared dx. So to save myself a little bit of time, I know what the antiderivative of 1 over x squared is. The antiderivative of 1 over x squared is negative x to the negative first, which I'll rewrite as negative 1 over x. And I need to evaluate that now from 1 to 10. So I have a negative 1/10 minus negative 1, well that's plus 1. So the area of that region is 9/10. All right, let's look at this one. It's the same function, 1 over x squared. And I'm saying let's find the area from 1 to b. I don't know what b is. I don't care. You know, in this piece here I said b was 4. Here I said b was 10. We can write a definite integral to find that area. It's just the integral from 1 to b, 1 over x squared dx. We know the antiderivative for 1 over x squared. It's negative 1 over x. So we have negative 1 over x evaluated from 1 to b. So that gives us a negative 1 over b minus negative 1. So that's negative 1 over b plus 1. So let's look at what we've done here. This is like a little formula, if you will, for any value of b. I know this little formula. So let's see, if I pick b to be 4, if I make b 4, b is 4, does this little formula, negative 1 over b plus 4, does it give us the same answer, 3/4? Yeah, it does. What if if b were 10? Well, if b were 10, it's this situation, b is 10. Does this little formula give us the area to be 9/10? Yeah, it does. So what if I said, you know what, I want b to be 100? Then we'd be integrating from 1 to 100. The area, we have a little formula to give us the area. It'd be negative 1 over 100 plus 1, which is 99 over 100. What if I said I wanted b to be 10,000? Well, this little formula would give us the area. And I believe that, negative 1 over 10,000 plus 1, I believe that would be 9,999 over 10,000. I think I'm starting to see the process on how to attack this improper integral. First off, I can't do it. I can't do this improper integral. That's okay to say I can't do it. What I can do is I can integrate from 1 to b, 1 over x squared dx. And then let b get incredibly large. Let b approach infinity. Well, we know what the integral from 1 to b, 1 over x squared dx is. We just did it right here. We just did that and we have negative 1 over b plus 1. The limit as b goes to infinity of negative 1 over b is 0. The limit as b goes to infinity of 1 is 1. This improper integral has a value of 1, which means the area of that unbounded region is 1. But this is how we're going to attack an improper integral. We're going to look at it and we're going to say, can't do it, going to rewrite it. Then we're going to do what's inside the brackets first, calculus, get an antiderivative, use the fundamental theorem of calculus, and after we've done that, we're going to take a limit. So at this time what I'm going to do is I'm going to say let's head back to the slides to kind of formalize what this process was meant to communicate to you. So let's head back to the slides and formalize how we attack an improper integral on the interval a to infinity. All right, folks, based on our work at the board, here's how we're going to attack an improper integral, specifically an improper integral on the interval a to infinity f of x dx. So first off, for our purposes, the function f, the integrand, is going to be continuous and non-negative for x greater than or equal to a. Then the improper integral from a to infinity f of x dx, as we just saw on the board, we're going to rewrite that improper integral as the limit as b goes to infinity, integral a to b f of x dx. And if that limit ends up existing, we're going to say that the improper integral converges. If the limit does not exist, we're going to say the improper integral diverges. So, this example, we're going to do 2 improper integrals and then just kind of compare the results. So in part A, we're going to integrate from 1 to infinity, 1 over x cubed dx. Part B, we're going to integrate from 1 to infinity, 1 over x dx. So make sure you have this in your notes because I'm heading off to the board to do the solution. All right, now that we know how to attack improper integrals, in this example, we were asked to evaluate these improper integrals. So in part A, the first one was the integral 1 to infinity, 1 over x cubed dx. So the first thing we say, can't do it. So we just rewrite it as integrating from 1 to b, 1 over x cubed dx. And then out front, we put the limit as b goes to infinity. So now we just attack what's inside the square brackets. So we attack what's inside the square brackets. So we have to integrate from 1 to b. I would rewrite 1 over x cubed as x to the negative third. Then we can use the power rule to get an antiderivative. Let's see, I add 1 to the exponent. And I have to put the reciprocal of the new exponent out front as a little multiplier. Evaluate from 1 to b. And I'm going to do one more little algebra step here. I'm going to rewrite this negative exponent as a positive exponent. So remember, I'm going to drop it downstairs. And, okay, so now I can use my fundamental theorem of calculus. So I have the limit as b goes to infinity, negative 1 over a 2b squared minus negative, as soon as I say minus a negative, I might as well make it a plus, 1 over, let's see, 1 squared is 1, 2 times 1, 2, 1/2. Now it's time to find the limit. Limit as b goes to infinity, negative 1 over 2b squared. Well, that denominator is getting incredibly large. So the limit is 0. The limit as b goes to infinity of 1/2. It's a constant. The limit of a constant is that constant. So the limit is 1/2. And remember, so the value of this improper integral is 1/2. And there was a vocabulary term that when the limit exists. We could say the improper integral, we could say that it converges. But the value of this improper integral is 1/2. So if you were to look at the graph of 1 over x cubed on the interval 1 to infinity, I mean, it looks something like this. So, matches up with the area of that unbounded region is 1/2. All right, let's look at part B. The improper integral from 1 to infinity, 1 over x dx. Can't do it. But I can integrate from 1 to b, 1 over x dx. And then I put the little limit as b goes to infinity statement out front. So let's see. The antiderivative of 1 over x. That's right, that's natural log, absolute value of x. Okay, since this interval, 1 to b, it only includes positive numbers. In my next step, I don't have to worry about including the absolute value anymore because all those numbers on that interval would be positive. So we'd have the natural log of b minus the natural log of 1. That's using the fundamental theorem of calculus. And I know what the natural log of 1 is. The natural log of 1 is 0. So this is the limit as b goes to infinity. The natural log of b, and this is one of those limits I said at the beginning of this section. Hey, we need to remember some limits that we've learned earlier in the book. Limit as b goes to infinity, natural log b, that limit is infinity, which tells us that this improper integral, the vocabulary term that matched up with it, was the word diverges. So what this means is if you look at the graph of 1 over x on the interval 1 to infinity, so here's the graph of 1 over x, it means that this unbounded region, well, it has infinite area. All right, so there are two examples. To make sure you understand the process of how to attack an improper integral, so before we start looking at how to apply improper integrals, I would like you all to do, here in section 7.6, I'd like you all to do number 15. So you know the drill. Pause the video, go do number 15, and when you're done with it, restart the video. I'll be here at the board working through it. Hey folks, number 15, you're asked to integrate from 1 to infinity e to the negative x dx. So hopefully you said, the first thing you said was, I can't do this. But instead, I can integrate from 1 to b e to the negative x dx. And then out front, you put this limit statement. Now you attack the integral that's inside. And let's see, the antiderivative of e to the negative x, well, that's just negative e to the negative x. Going to evaluate that from 1 to b. So you have the limit as b goes to infinity, negative e to the negative b minus negative, well, minus negative, it's plus, e to the negative first, and you know, I could rewrite this if I so desire as negative 1 over e to the b plus 1 over e. So I could get rid of those negative exponents, drop them downstairs, make the exponents positive. So now the limit as b goes to infinity, negative 1 over e to the b. Denominator getting incredibly large, so this limit is 0. 1 over e is a constant. So the limit as b goes to infinity of a constant is that constant. So the value of this improper integral is 1 over e. And if we wanted to, we could say the improper integral converges, and it has a value of 1 over e. So hopefully you're able to get that. Hopefully you're following the process I'm setting up here. It's a pretty simple process to follow, but you know, it it makes more sense if you write it down in a very logical way. Well, now let's see what's up next. So going to head on back to the slides. All right, hopefully you saw in that example parts A and B, attacking improper integrals aren't too bad, and hopefully you were able to do number 15. So let's continue on where, next up will be how can we apply this concept of an improper integral? How can we apply it in a real world situation? So even though Objective 4 says we're going to estimate total oil well production, we're not looking at an oil well here. We're looking at a maple syrup farmer. We get maple syrup from a maple tree, and a maple syrup farmer has determined that a maple tree will produce syrup at a rate given by m of t equals 15.5 e to the negative 0.11 t. So that's a rate function. T is the number of years since the tap has been installed on the tree, and m of t is measured in gallons per year. See, it's a rate function. Estimate the total amount of maple produced by this tree. So to get a total amount, it's that same old concept. We integrate the rate function to give a total amount. But since we want to know the total amount, not just the total amount produced for, say, the first 5 years or the first 8 years, we want to know the total amount produced. So this is going to give rise to an improper integral that I'm going to head off to the chalkboard to evaluate. All right, folks, this example, I'm not going to read all the words. It's a maple syrup farmer. This was the function. M of t was 15.5 e to the negative 0.11 t, where m of t was measured in gallons per year. So we're asked to estimate the total amount of maple produced by this tree. So folks, you're given a rate function. To get a total accumulation, you integrate the rate function. So we have to integrate the rate function, and the limits of integration, well, the limits of integration are 0 to infinity. That's the total amount over the lifetime of the tree. If we had said, what's the total amount of maple produced by this tree over the first 5 years, then you'd be integrating from 0 to 5. But it just says estimate the total amount of maple produced by this tree, period. So we have to attack this improper integral, which we can't do, but we can do this. We can integrate from 0 to b. So that's how we rewrite it. And out front we put the little limit statement. Now we do the calculus inside the brackets. And, well, again, this is a very, very friendly antiderivative, as long as we remember that little rule, that little formula that we saw back in chapter 6. We immediately get 15.5 over negative 0.11. And evaluate that from 0 to b. So that gives us the limit as b goes to infinity. All right, so now we use the fundamental theorem of calculus. So we'd have e to the negative 0.11b minus, well, that's going to be negative. Positive divided by a negative is negative. So it's minus a negative, make that plus, 15.5 over 0.11 e to the, now when 0 comes in here for t, that exponent's going to become 0. So pulling the problem up here, and let me just rewrite it. I'm going to take this e to the negative 0.11b and I'm going to move it downstairs to make the exponent positive. . And remember, e to the 0 is 1. So that leaves me with just 15.5 over 0.11. Now let's do the limit. The limit is b goes to infinity. See, this first term, this denominator is getting incredibly large. So that means 15.5 divided by an incredibly large number, well, that's going to be 0. This is a constant. The limit of a constant is that constant. And if you use your calculator now to do 15.5 divided by 0.11, you're going to get 140.90, and I think the 9 zeros repeat. So let's answer the question though. Estimate the total amount of maple produced by this tree. Well, I guess you could say about 140.9 gallons, or if you wanted to round it to the nearest whole number, that would be cool. You could say 141 gallons. So there really wasn't much new in this example. The only new part was we had an improper integral. Everything else was kind of old in the sense that we were integrating a rate function. So let's head on back to the slides and see what's next. All right, folks, next up, let's just remember the formula for a continuous income stream. It's the formula for the present value of a continuous income stream. P equals the integral 0 to t f of t e to the negative rt dt. We just saw that in section 7.4. Remember, f of t is the rate of flow function. P's the present value. R is the interest rate, compounded continuously for t years. So that's just a quick, reminder of what we did in section 7.4. This thing called capital value of a continuous income stream, it is nothing more than the present value on the interval 0 to infinity. So in other words, we integrate 0 to infinity f of t e to the negative rt dt, and that gives us what is called the capital value. So in other words, capital value can tell us how much something is worth, which would be important to know if you want to buy something, a business, let's say, or if you want to sell something, a business, let's say. So why don't we go to the book and let's do number 52 on page 586. So I'm going to head off to the chalkboard to do number 52 on page 586. All right, hey, number 52 here. It says Ginger owns a rental property that generates an indefinite annual rent of $6,000. Determine the capital value of this property at an annual interest rate of 8.5% compounded continuously. All right, so this rental property that has an annual income of $6,000, that's basically telling you that f of t is 6,000. That's the rate of flow function. So capital value, well, capital value is nothing more than integrating, doing that present value on the interval 0 to infinity. So this is something that we saw introduced in section 7.4. So you have your rate of flow function, e to the negative, and the rate was 8.5%, so that's 0.085 t dt. This tells us the capital value. Capital value, in a way, think of capital value as being what's it worth? What's its value? What's it worth? So if Ginger wanted to sell this rental property, what would be a good selling price? Or if you wanted to buy it, what would be a fair price, to buy it? So in any event, here's an improper integral. We know we can't do it, but we know we can integrate from 0 to b. And out front, Put that in square brackets. Out front, we put the limit as b goes to infinity. Then it's a Nike problem. Just do it. So the antiderivative of 6,000 e to the negative 0.085 t, that antiderivative is 6,000 over negative 0.085 e to the negative 0.085 t. Evaluate that from 0 to b. And I'm going to pull it up here. So crank this through the fundamental theorem of calculus, put the b in, and you put the b in, you get 6,000 over negative 0.085 e to the negative 0.085 b minus, so now the 0 goes in, so the exponent becomes 0. This quotient's negative, so minus a negative is plus 6,000 over 0.085 e to the 0. So we have the limit as b goes to infinity. See, 6,000 over negative 0.085 e to the positive 0.085 b plus, and remember e to the 0 is 1. So doing the limit as b goes to infinity. We've seen this a lot now in this section. This shouldn't be a surprise to you. The limit as b goes to infinity of this first term is 0. If the limit as b goes to infinity of a constant is that constant. And if you take 6,000 and divide it by 0.085, you get 70,588.24. That's the capital value of this rental property. So to make sure you understand how to do a capital value problem, which is just an application of an improper integral, and along with something old that we learned back in section 7.4, I would like you now to do, here in section 7.6, number 51. So pause the video, do number 51. Once you've completed it, restart the video, and I'll be here at the board working through it. Hey folks, here at number 51, Ellie owns a rental property that generates an indefinite annual rent of $10,000. That means the rate of flow function f of t is 10,000. Determine the capital value on this property at an annual interest rate of 6%, compounded continuously. So capital value, it's integrating present value over the interval 0 to infinity. So here that's 10,000 e to the negative, see the interest rate was 6%, dt. It's an improper integral. We should know by now you rewrite the improper integral as integrating from 0 to b. And out front, put that in square brackets. It's the limit as b goes to infinity. It's a very easy antiderivative, just 10,000 over negative 0.06. And evaluate that from 0 to b. Use the fundamental theorem of calculus. So the b comes in first, so you have 10,000 over negative 0.06 e to the negative 0.06b minus the 0 comes in. Again, this quotient's negative, so minus a negative, I'm going to rewrite that as plus 10,000 over 0.06 e to the 0. We know e to the 0 is 1. So we have the limit as b goes to infinity, 10,000 over negative 0.06 e to the positive 0.06 b. And the limit as b goes to infinity of this first term is 0. The limit as b goes to infinity of a constant is that constant. And if we use our calculator and do 10,000 divided by 0.06, we get the capital value to be $166,666. It's kind of evil. And 67 cents. So there's an application of improper integrals, computing a capital value. So let's head on back to the slides, and I think we have one more type of application we're going to look at. All right, after doing 52 as an example, and then you did number 51, let's look at another area that we can apply an improper integral. So again, recall the formula for the present value of a continuous income stream. You know, we just reviewed this before the last example, and that's from section 7.4. I just thought I would write it down again. Any fund that creates a steady income stream, well, we can give it a name of it's being called a permanent endowment or a perpetuity. Endowments, perpetuities, these are often seen in scholarship funds. You know, someone wants to have a scholarship fund bearing their name, and they want to fund it forever. So say it's a $2,000 annual scholarship bearing their name. They want to fund it forever. So the question is, how much money would you have to invest today to fund this scholarship forever? So to see how to do this, we are going to go to your book, and we're going to do number 62 that's on page 587. So here we go to the chalkboard. All right, we're going to look at something that's called an endowment or a perpetuity. Number 62. Let's see. The Beagle Works Company has decided to provide an annual scholarship in the amount of $10,000 to individuals studying veterinary medicine. If the annual rate of interest is 7.75% compounded continuously, how much should be invested to fund this scholarship perpetually? In other words, to fund this scholarship forever. All right, so let's see. We know the rate of flow function is 10,000, so I went ahead and I wrote that down. F of t is 10,000. So it's that old present value type problem, except we're integrating on the interval 0 to infinity. 10,000 e to the negative 0.0775 t dt. It was 7.75% interest compounded continuously. And out front, we know to put the limit as b goes to infinity. And we should be dialed in. Easy to get an antiderivative. 10,000 over negative 0.0775 e to the negative 0.0775 t. Evaluate that from 0 to b. Oops, made a typo at the board. That should be a b. And I'll go ahead and put in the fundamental theorem of calculus. So b comes in here, so you have 10,000 over negative 0.0775 e to the negative 0.0775b minus, now the 0 goes in, and again this quotient's negative, so minus a negative, so that's plus 10,000 over 0.0775 e to the 0. I'm going to cut to the chase. I'm not going to write down this next step. We've seen it a lot that the limit as b goes to infinity of this first term here is going to be 0. E to the 0 is 1. This is a constant. The limit as b goes to infinity of a constant is that constant. And if you use your calculator and do 10,000 divided by 0.0775, you get $129,032.26. So if $129,032.26 is invested today at this fund that earns 7.75% interest compounded continuously, it will fund this $10,000 annual scholarship forever. Kind of cool, kind of trippy. That's it for section 7.6. So at this time, you should turn off the video and go do the exercises in section 7.6. Thanks for watching.